Okay, let's cover section 4.1. Section 4.1 is on the basics of differential equations. Okay, the basics of differential equations. Okay, let's throw up a definition. A differential equation is any equation that involves one or more derivatives of an unknown function. Okay, so differential equation is an equation that has derivatives in it. Okay. And then usually we want to try to solve the original function or the parent function that that the derivatives were derived from. Okay, let's look at how differential equations behave. Okay, number one, verify that the function y equals e to the negative 3x plus 2x plus 3 is a solution to the differential equation y prime plus 3y equals 6x plus 11. We want to verify that this guy is a solution to this differential equation. Why is it a differential equation? Because it contains a derivative. It contains the y prime here. Okay, that's the derivative, that's the differential equation. Okay, so what I need to do is I need to figure out, well, what is y and what is y prime? So I'm going to take the derivative of the original function, that is the solution. So y is equal to e to the negative 3x plus 2x plus 3. And I'm going to find that derivative. I'm going to find that y prime. Okay, and if I take the derivative of e to the 3x, it's negative 3 e to the negative 3x. Okay, that's the chain rule. Derivative of the outside is the e, which is just itself. And then the derivative of the inside is the negative 3x, which gives me that negative 3 and then plus 2. Okay, derivative of 2x is 2 and derivative of a constant is 0. So now what I want to do is I want to plug in both y and y prime and see if this creates an equality. So we have negative 3x, or sorry, negative 3 e to the negative 3x plus 2. That's my y prime. Plus my 3y, but what was y? Y was, I'm plugging it into this equation here. Okay, this was y prime. This is going to be 3 times y, which is e to the negative 3x plus 2x plus 3. So that's y. And we want to know, does that equal 6x plus 11? So let's distribute the 3 here and then combine some like terms. E to the negative 3x plus 2 plus 3e to the negative 3x plus 6x plus 9. Does that equal 6x plus 11? Okay, and the negative 3 e to the negative 3x and the positive 3 e to the negative 3x, those are going to cancel. I will combine the 2 and the 9, and I get 6x plus 11, and so it does check. Okay. So yes, y equals e to the negative 3x plus 2x plus 3 is a solution to the differential equation y prime plus 3y equals 6x plus 11. Okay, let's look at a definition. Okay, the order of a differential equation is the highest order of any derivative of the unknown function that appears in the equation. Number 2. What is the order of the following DEs? Okay, and if you see DE, it just means differential equation. It's just a shorthand for a differential equation. Okay, what is the order of the following differential equations? So we're looking for the highest derivative. Okay. Okay, so for A, we have y prime minus 4y equals x squared minus 3x plus 4. Okay, and this is a first derivative is the highest derivative, the highest order of any derivative. Okay, this only has a first derivative. It has the function and the first derivative, so this is called a first order differential equation. Okay, B, x squared y triple prime minus 3x y double prime plus x y prime minus 3y equals the sine of x. Okay. So this has a function has a first derivative, a second derivative, and a third derivative. So this is called a third order differential equation. The highest derivative is 3. Okay. C. Let's look at 4 over x, y to the fourth derivative. Okay, the fourth derivative of y minus 6 over x squared, the second derivative, plus 12 over x to the fourth y equals x cubed minus 3x squared plus 4x plus 12. This is a fourth order, okay, differential equation. Okay, or we could call it order 4. Okay, differential equation of order 4. Okay, or fourth order differential equation. Okay. Okay, let's talk about general versus particular solutions. Okay, general versus particular solutions. Okay, for y prime is equal to 2x, the general solution is y equals x squared plus c. Okay, we could easily get that from integrating, okay, 2x, right? If we integrate 2x, we could get x squared plus c, right? And so we say, okay, y equals x squared plus c. If I take the derivative of that, I get y prime equals 2x. This produces, because of that constant, it doesn't produce just one curve. It produces what's called a family of curves, okay? It's an infinite number of curves that are all shifted, same shape, but all shifted in the y direction. Okay, this, which produces a family of curves since every derivative of x squared plus c is 2x regardless of what the value of c is. Okay, and so what this looks like is, if I were to let c be integers, okay, if c is 0, if I have y equals x squared plus c as my family of curves, this guy here, okay, which is my solution to my differential equation, it just is an infinite number of solutions because of that constant. If I were to just sketch a few of these, right? Um, this would be when c is 0. This is y equals x squared. And then if I were to sketch another one, this would be, right, y equals x squared. Oh, mushy. Okay, this is y equals x squared plus 1. We could do y equals x squared plus a half. We could do, we could get a family of curves like so. It really depends on what the constant is. It produces, okay, the same shape, but it just, right? So this would be like if it was, okay, y equals x squared minus 1, right? So same shape, just, different y-intercept. Okay, the only thing that's changing here is the y-intercept. One is 0, one is -1, and one is 2. And so it gives me a family of curves. I could put in any y-intercept I want. Okay, any y-intercept I want, and it would produce this family of curves. And that's referred to as the general solution. The general solution produces a family of curves. For y equals 2x, sorry, for y prime equals 2x, y equals x squared minus 3 is what's called a particular solution. A particular solution. It is one curve picked out from the family. It's one particular solution. Okay. It's a particular solution for the differential equation. In order to find the particular solution, we need to give a specific point. Sorry, we need to be given a specific point on the curve we are looking for. And this is sometimes called an initial condition. We need to know a value that is going to be on the curve so that we can isolate which specific curve we're looking for. Okay, so let's look at an example here. I'm going to change this to plus 3, if that's okay with you. Is that cool? You can go to plus 3. Because I just want to be consistent here.
Yeah, I'll be all right.
Okay. I'll change that in my notes. Okay. Number 3. Find the particular solution for y prime equals 2x, which passes through two, 7. Okay, the 0.27. Let's find a particular solution for this, which passes through 0.27. Okay, so what was the solution to this? It was a family of curves. We take the integral. Okay, if we integrate this, we get 2x, the integral of 2x being x squared plus c, right? So now what I'm going to do with this value, this point that I've been given, that's going to help me solve for my constant. So I'm going to plug in the y value of 7. I'm going to plug in an x value of 2. And I'm going to solve for my constant. So we get 7 equals 4 plus c. Subtract 4. And c equals 3. So my particular solution that I'm looking for is y equals x squared plus 3, which is a parabola. It just happens to have a y-intercept at 3. And that's my particular solution. And y squared, y is equal to x squared plus 3. Okay, so this is the particular solution of the differential equation y prime equals 2x that goes through 0.27. Okay, let's talk about an initial value problem. Initial value problems. Initial value problems, or initial values, are ordered pairs used to find the particular solution to a differential equation. The number of initial values needed is equal to the order of the DE. Okay, the number of initial values that we need is going to be equal to the order of the differential equation. Meaning that if it's a first order differential equation, I only need one initial value, I only need that 1 point. If it's a second order differential equation, I need 2 values. They could be either of the function itself or of subsequent derivatives. Okay, but the number of values that you give me has to be equal to the order. If it's a third order, I would need 3 initial conditions and initial values, or sometimes they're called initial conditions too. Initial values. I'll put in here conditions. Sometimes they're called initial conditions. Okay, initial values or conditions. Okay. So let's look at a problem, an initial value problem. Number 4. Find the particular solution to the differential equation y double prime is equal to 6x. Given, and here, how many initial values, initial conditions do I need to solve this?
2.
2, yeah, very good. Thank you. Yeah, 2. Because it's a second order, I need 2 initial conditions. I could either get 2 points on the solution to the differential equation, or you could give me 1 point on the solution and 1 point of the first derivative. And that's what we're going to be given here. Okay, so we're going to have y of 0 is equal to 5, and y prime of 0 is equal to 7. Okay, so we're going to have the initial value at 0, the value of we're given the value of the function, and then at the first derivative evaluated at 0, the value of the first derivative, or the slope of the tangent line of the function at 0. So we're given information about the solution, and we're given information about its first derivative in order to solve this second order differential equation. So let's do this. Let's take the integral of both sides here. I get the integral of a second derivative is going to be a first derivative. That's going to be equal to 6x squared over 2 plus c. Okay, and I'm going to call this C1, because you'll see in a second why I need to call it C1, because I'm going to end up with another C. Okay, I'm going to end up with another constant. Now let's do the same thing. Let's integrate the y prime equals, this is going to be 3x squared plus C1. Let's integrate this guy and see what we get. The integral of 3x squared is going to be 3x cubed over 3 plus c1x plus c2. Okay. So y is equal to x cubed plus c1x plus c2. But now, how am I going to figure out what c1 and c2 are? Well, I'm going to use my initial values. I'm going to say, oh, okay, well, I know that y of 0 is going to be equal to 5. So if I plug in zeros here, it tells me that C2 is equal to 5. Just plug in zeros. Let's say, okay, 5 is equal to 0 cubed plus C1 times 0 plus C2. Okay, so this is going to be 0, 0, C2 has to be 5. Okay, it's good to know. Okay, what else do I know? Well, I know that the first derivative at 0 is equal to 7. Okay. Now, what was the first derivative? The first derivative was 3x squared plus c1. Okay, so if we plug in a 0, right, then we're going to plug in 0 there. That's going to go to 0. This has to equal, let me equal to 7 here. Okay, 7 is going to be equal to 3 times 0 squared plus c1. So c1 had to be 7. So the solution, the particular solution here to my initial value problem is going to be x cubed plus c1, which is 7x. I'm looking right here. Okay, plus 5. And that's the particular solution to my differential equation, given my 2 initial conditions. Okay. And that is section 4.1.